In evolutionary biology, organisms must constantly adapt just to maintain their survival in a changing environment, a concept known as the Red Queen hypothesis. What happens when we apply this same relentless adversarial pressure to large language models writing computer code? This paper introduces the digital Red Queen, an algorithm that explores adversarial program evolution within the classic programming game known as Core War. Most current methods for evaluating code generation treat problems as static puzzles with a single correct answer. However, the authors argue that this misses the reality of domains like cybersecurity, where the environment is dynamic and adversarial. To study this, they invoke the Red Queen hypothesis, suggesting that an AI agent must constantly evolve its strategies simply to survive against opponents that are also adapting. To test this hypothesis, the researchers utilized Core War, a programming game that serves as a perfect volatility sandbox. In this environment, assembly programs called warriors fight for control of a shared memory block where code and data coexist. Because warriors can overwrite each other's instructions directly, survival requires robust strategies that can withstand active sabotage, making it an ideal testbed for adversarial evolution. The core contribution of this paper is the digital Red Queen algorithm, or DRQ. Unlike standard self-play that only looks at the most recent opponent, DRQ forces new warriors to optimize their fitness against the entire history of the lineage. The system uses a large language model, not as the agent itself, but as a mutation operator that rewrites the assembly code to solve the increasingly difficult problem of beating every ancestor. Let us look at the empirical results to see how this historical pressure shapes the resulting software agents. The plots presented here illustrate the trajectory of the evolved warriors over multiple rounds. The authors observed that while the variance in behavior decreased, meaning warriors converged on optimal strategies, their ability to defeat unseen human opponents, labeled here as generality, consistently increased. This indicates that training against the full history creates robust generalists rather than brittle specialists. A fascinating disconnect emerged between the code and its behavior, mirroring convergent evolution in biology. While the source code, or genotype, remained highly diverse across different runs, the phenotypic behavior converged on nearly identical survival strategies, such as aggressive thread spawning. The researchers highlight that widespread optimal behaviors surface, regardless of the distinct underlying code implementations. This paper demonstrates that by using large language models to drive adversarial evolution against a deep history of opponents, we can generate robust programs that break out of the cycles typical of static optimization. For more details on the digital Red Queen and Core War dynamics, I encourage you to read the full paper.